We've really only discussed the first postulate of quantum mechanics, and I'd like to discuss some of the others at least briefly. If we have one state like that, I have a physical interpretation of that. That is a photon that has a horizontal polarization. And here's a different state. Here is a photon with a vertical polarization. Now I know how to physically interpret those, but even that is kind of difficult. Supposing I was to have a laser device. Here we go. Here's my laser device. And it's going to emit a laser beam. And I'm going to put my laser beam through some polarizer. Now polarizers have some direction. Here we go. And then on the other side of that laser beam, I'm going to put a detector. And it's a perfect detector, so if my photon goes through my polarizer, I'll get a click. And if the photon does not go through my polarizer, I will not get a click. Now, if this is a vertical polarizer and I put this through, I'm going to get a click every single time. And if I put a horizontal one through, I will never get a click. That's all fine. Remember, however, that if I was to build this device classically, then classically I wouldn't be describing single photons, I'd be describing this as an electric field with a particular polarization. And if it had a vertical polarization and I was to put it through something with, say, a 45-degree angle, then if here I had the intensity I, if the angle of the polarization from here and the polarizer was an angle theta, then here, so here I've got intensity I, here I would expect to have intensity, maybe this would be I naught cos theta, cos squared theta in fact. The electric field would go as the electric field cos theta, so the intensity goes as cos squared. So in fact, I've got an equal amount of light being absorbed and passed through if I'm at 45 degrees, and none if I'm at right angles. So that's what happens to a field. What happens to a single photon? Supposing I have something like this and I pass it through something at 45 degrees. Half my photon can't go through. It can't go click and not click. So what actually happens? And the answer is, of course, random things happen. The universe seems to roll some dice and my photon either goes through or doesn't. And this measurement postulate, which we'll examine a lot more in the next lecture, is kind of at the heart of quantum mechanics and the heart of why quantum mechanics is sort of counterintuitive. Let's look at some other states. Psi3 is going to be a linear combination. Any linear combination of these two is fine, provided I'm normalized. So a physical state, we normally have to write it in a normalized fashion. So if I have my horizontal plus my vertical, provided I got my 1 root 2, that's normalized. Or I could write a different one. I didn't have to write plus, I could have written minus, so let's do that over here. And in fact, I didn't have to write a real number, I could have written complex numbers, so let's do states like that. Now we understand these top two, Psi1 and Psi2 physically. What about Psi3 and Psi4? Well, it turns out they correspond to the 45-degree angle polarizations respectively. And we could have written our photon in terms of a superposition of these two, because this is actually a basis. How would I show that Psi3 and Psi4 are a basis? I've got a few ways. The first is, I know that these two are a basis, form a basis, so if I could show that I could write H as a linear combination of these two, which would be the sum, and V as a linear combination of these two, which would be the difference, then I know that this must be a basis. Another way of doing it is a result from linear algebra, where I know that if I have a set of linearly independent vectors of the same dimension as my Hilbert space, then they must form a basis. And because I know that this is a two-dimensional Hilbert space, the fact that these two are in fact orthogonal means that they're linearly independent, and they are in fact normalized as well, so this is an orthonormal basis for my Hilbert space simply because there are two of them. And both of those arguments apply equally well for 5 and 6. These are actually the circular polarizations. So you can describe the polarization of a photon with just two complex numbers, but you can do it in different bases. You can do it in circular polarization, polarization at different angles, or horizontal and vertical. And you can do non-square things as well, which would give you elliptical polarizations. So we could write an arbitrary state of a photon in terms of linear combination of Psi1 and Psi2, or we could write it as some different linear combination of Psi5 and Psi6. And the next lecture we'll learn ways of calculating C5 and C6 out of alpha and beta. For now, let's turn our attention very briefly to linear operators. So if I wanted to write an operator that acts on this thing, a completely general one, If I were to say pick this basis, I think, alright, well if I could write that like that, then a completely general linear operator would look like a matrix with 4 numbers acting on that, and that would give me a completely general linear operator, give me a vector back. What does that look like in this kind of form though? So this element here is the element that acts on the psi1 term and gives you back a contribution to the psi1 term. And what that would look like is some kind of number. So if this was A11, that would look like this term, A11. It's got to act on this bit. It's got to give me nothing with respect to that, but it's got to give me this bit. So if I write this, psi1, psi1, so this is the ket and the bra. If I act that on psi1, let's look at what happens. If I act that on psi1, these two are going to give me, because they're normalized, that's going to give me 1, and so this will be equal to, so this acting on psi1 will be just A11 psi1. And so you can see that will give me the right term in this vector. And so in fact, these 4 terms can be written like this. A completely arbitrary operator acting on this space would look like some complex number times this ket and this bra plus another complex number, this one. Now this one's going to take psi2 and turn it into psi1. So there's my psi1. It's going to interact with psi2 and so on. There you go. And next lecture we'll talk about easy ways of showing this kind of relationship and working out that kind of relationship.